Hi, I'm Kishore, an intern with Sun Labs working with Dr. David Engrove on the project the Adaptive Power Management. Today I'll talk about the initial step we have successfully completed of our project, that is developing simple and robust power models using performance monitoring events for AMD Quad-Core OpenSolaris systems. The basic idea is correlating power consumption with performance monitoring events. Actually, developing power models using performance events is not a new idea. But unlike previous studies, our work is different in terms of giving the following contributions. The first one is we showed a methodology to implement simple means here with fewer events, performance events, and robust power models which can predict power consumption with greater than like 95% prediction accuracy for most of the benchmarks. And number two is this model works for across multiple frequencies supported by the CPU. And number three is we used appropriate model selection and model assessment techniques for assessing the model as well as for finding the best predictors of the model. And the last one is, as we developed power models with fewer events, those events are widely available on almost modern platforms. Our methodology is portable across all modern platforms. I will next talk about the experimental environment. Basically, we used two systems. One is AMD Phenom system and another one is AMD Shanghai. This is the Shanghai system. It as a quad-core system, it supports 4 frequencies: 2.6, 1.9, 1.4, and 0.9, and it has 6 MB L3 cache and as well as 4 GB RAM. And we have another system, AMD Phenom. This is AMD Phenom. It's a naked system now. It supports 2 frequencies, 2.4 and 1.2, and it has 2 MB L3 cache and 2 GB RAM. Basically, we used CPU track command to read the monitors, and we used X-Tech power meter to measure the power consumption of the system. This white cable is the RS-232 cable, which is used to read the power samples. Okay, now I will give you a brief idea about our methodology. Okay, our methodology is very simple. Take all the available events available in the system. Actually, AMD's processor provides around 134 performance events. Based on the literature, initially we considered 8 performance events. These 8 performance events. The events are like unhalted cycles, instructions, mispredicted branches, rotated branches, L2 cache misses, L3 cache misses, CPU dispatch stalls, and retired micro operations. We derived predictors from these events by dividing the total number of events by execution time of the workload in terms of tick. Here, one important point is the clock tick is independent of frequency in AMD systems. That means the duration of the clock tick equals to the CPU cycle when the system is running at highest frequency level. And okay, initially we used these 8 predictors to build the model. A linear model. We used regression method LM of R statistical language. Using that method, we built 8 predictor linear power model, as well, Phenom as well as Shanghai. And how we collected the data? Actually, we ran the benchmarks, spec CPU 2000 benchmarks, and for 4 times each benchmark. Basically, Phenom supports 2 frequencies. We consider each run as a data point. So, as Phenom supports 2 frequencies, we have 176 data points in case of Phenom system, and we have 352 Shanghai data points. On these data points, we applied the regression method, LM method, and we build the 8 predictor linear power model, Phenom as well as Shanghai. Here, to assess the model, we used 2 testing techniques. One is called cross-validation technique, leave out one cross-validation technique. Another one is called testing the model against new test data. Considering our methodology, I explained about the first step. The first step is take the all available events. Here we have 8 events. Take the all 8 events, build the regression model. Take all reasonable events. So we have taken 8 events and we build the regression model. Then use the cross-validation test as well as new test data to test the model, to assess the model, and use any reasonable metric to find the error prediction accuracy of the model. Next step is finding the most important predictors among these 8. So for that we used relative importance measures method, RAM method, basically model selection method. The RM method produced 2 important predictors in terms of R-squared value. Higher R-squared value means the most important predictor. So the RM method showed that the L3 cache misses and the unhalted cycles are most important predictors among these 8 predictors. Actually, it makes sense from computer architecture point of view also, because we trained the data on spec CPU 2000 benchmarks, and the spec 2000 benchmarks stress CPU and main memory. Basically, the unhalted cycles reflect CPU utilization, and the L3 cache misses reflect memory boundedness of the application. So basically, from the statistical point of view as well as from computer architecture point of view, these two predictors are very important. And one more important point is by producing a model with these 2 events, eliminated the issue of multi-collinearity. Basically, a good model means the predictors or inputs of the model should be highly correlated with the target parameter. In our model, the target parameter is power consumption, and the other 8 predictors are the inputs. So, in the 8 predictor model, the multi-collinearity, we used a method called variation inflation factor, VIF method. That VIF method value in case of 8 predictor model is greater than 30 almost all the 8 predictors. That means in 8 predictor model, there is a multi-collinearity issue among the predictors. So it's not a good model. But in case of 2 predictor model, we got value of 1. Variation inflation factor value, we got 1. That means the model is more robust comparing with 8 predictor model. Okay, in conclusion, we showed a methodology for developing simple and robust power models using performance events for latest AMD Quad-Core systems running OpenSolaris. The models predicts power consumption greater than with 95% prediction accuracy for most of the benchmarks, and the models works across multiple frequencies, and the methodology is portable because the fewer events, the 2 events are available in all modern hardware platforms like unhalted cycles and L3 cache misses. As future work, we want to plug these models into Solaris kernel, and we want to use these models for smart dynamic frequency scaling techniques to optimize power consumption. And one important limitation of our work is as we develop the models on spec CPU 2000 benchmarks, and these benchmarks only stress CPU and main memory, you can expect that the models work well for the workloads which stress CPU and main memory. Of course, if you want to use models, if you want to use workloads which stress disk and IO, just you need to add the events which reflect the usage of disk and IO to this model. Overall, the methodology is very simple, and it's very useful for the research community. Thank you.